Hey there, folks. Let me get things arranged here real quick. I'm using a different laptop, and so I'm having to learn this, software slightly different and everything, but I think we're doing okay. I guess that is fine. Sure. Okay. Let's pick up. I haven't had a chance to look at those tests yet. I do want to take a look at them and see how we did. I'm sure you want to know how you did too. But let's talk about the kind of problems that we have to work in class on Thursday. We're going to start with counting techniques. Now I know that sounds perhaps a little strange. I'm not really talking about counting, 1 to 10 per se. But we will. It is a matter of counting things up. How many ways can certain things happen? And so many of these initial things we're going to talk about, I think are things that you probably have heard of. I'd like to start with one of the easiest ideas, and that is the fundamental theorem of counting. Which I think you'll probably recognize once we start to mess with it. Let's suppose that a procedure or a task, or I'm sorry, yeah, I'll stick with procedure. A procedure consists of two discernible tasks. That means you can tell them apart. And that there are M ways. I'm shaking the table a little bit. I'm sorry about that. There are M ways to do the first task. And N ways to do the second task. Then what the fundamental theorem of counting tells us is that there are M times N ways to conduct the entire procedure. Okay, and that is the fundamental theorem of counting. I would say to you that this can be extended to more than just a procedure with two tasks. And we would do that, if we were really, being strict here, I would show you the induction proof of it, but I think you can kind of see where we're going. To a procedure with any finite number of tasks. We take the first one and then say, suppose it works for K tasks, and then you add one more and apply the first one. So it's not hard to do. So I'll restate it for us though. The extended theory of counting suppose we'll insert a number of things. That a procedure consists of n discernible tasks, and that there are m sub k ways of doing the kth task. Then there are M1, M2, all the way out to M sub n ways to conduct the procedure. Okay. Probably don't need too much convincing on this, but you know, if you want just a very simple example, if you have three pairs of socks, 4 pairs of pants, and 6 shirts, I'll throw this in for my wife's sake, all compatible. Then how many outfits, oh, can't spell outfits, sorry. Are possible. Well, I wish I could move that thing. I guess this thing is just part of the deal, so I'll leave it alone. But you think about having different slots that need to be filled here, right? You've got your socks you got to pick out, and you've got your pants that you have to pick out, and you got your shirt. And then, so how many choices do you have? Well, you got 3 for the sock, and 4 for the pants, and 6 for the shirts. So what is that? 1272. Okay, and you think about it, you could actually write all these out. You know, you could take 1 pair of socks, 1 pair of pants, and then list each of the 6 shirts. And then keep the same pair of socks, different pair of pants, and then list out the other 6 shirts. You could actually list out, with a number that small, all the different possibilities. Shirt 1 through shirt 6, you know, and pants 1 through pants 4, and socks 1 through socks 3. You could write them all out. That's not practical in a lot of cases. Let me give you a slightly different example that's a little more in the mindset that we're going to use it. Telephone numbers in North America. I've had to follow certain conventions through the years. Excuse me. at one time, the first number of the area code and the first two numbers of the 7-digit number couldn't be zeros or ones. Also, the middle digit of the area code had to be either a 0 or a 1. Now, you know that's changed. We're in a 270 area code now, right? But this is the way it used to be. Like 502 and 606 and things like that. Remember those area codes. So the question is, how many different phone numbers were possible under this setup? Now, we're talking about things. We have actually discernible tasks. We've got like the first number of the area code. We've got the second number of the area code that we're picking. So the fact that these things are falling into a particular order makes them discernible. Okay. We have a number of choices that we can reuse. The numbers don't have to be distinct numbers, right? You can have a 555 prefix on your 7-digit number, things like that. So you can reuse the 5s. So the way I tend to think of this is, okay, let's fill in the blanks here. There's the area code. 7. First, the 3 number prefix. Okay, and let's think about how many things are possible. Now, under this particular scheme, the first number of the area code and the first 2 digits of the 7-digit number could not be zeros or ones. We've got 10 digits including the zeros and ones, 0 through 9, right? But we cannot use 0 and 1, so that leaves us with only 8 choices in these positions. So 8 choices here, and I know I put them above earlier, but I tend to put them below. I was just out of paper when I did a second ago. So, the first number of their code and the first 2 digits, so 8 choices here, 8 choices there. And then the first 2 digits of the, the middle digit of the area code had to be either 0 or 1, so we have only 2 choices there. And then everything else, we've got 0 through 9. So 10 choices there, 10 choices here, 10, 10, 10, and 10. Okay? And so the fundamental theorem of counting tells us, and it's actually the extended theory of counting tells us, okay, then the number of ways to conduct this procedure of selecting all these numbers is to multiply all of these numbers together. Okay, so what is this? We've got a 2, I've got 8 cubed, and 10 to the 1, 2, 3, 4, 5, 6. Okay. So let's see, 2 and then 8 cubed, I'm pretty sure is 512. And then that's a million. Right, 6 zeros. So this would be 1024 with 6 zeros behind it. Okay, and now, and so that's a pretty big number. It's 1,024,000,000 different phone numbers. That gives you an idea how many numbers are in use today, right? Because we've had to ditch some of these conventions, particularly this middle digit being a 0 or 1. We live in a 270 area code for the most part. So that, replace this 2 with, I think it's now everything, so 10, you can see, or multiply by another 5, so you'd have 5 times this many numbers now available to us. But that's a great big number, and we still needed more, so it's pretty scary when you stop to think about it. So when we're doing counting then, so what I'm going to try to do is get all of our techniques kind of categorized where you can keep track of them. If we're looking here at a length, can't spell length, sorry, length R, arrangement. Now arrangement means that order matters of n items, and these are distinguishable items. And I can have repeats. Okay. Which is what a kind of, that would be this kind of situation right here, where I've got arrangement of a certain length, and I've got n choices for each thing, and they're distinguishable choices. Then that's, you got the R slots, right? N times N times N, R times. So this is N to the R. Okay. If we instead have choices that once I use them, I cannot reuse them. Okay, so this would be a length R arrangement of n items. And again, things I can tell apart. Without repeats, then this changes slightly. Now I got n things in the first slot. I'm sorry, I tend to put this, let me do it the way I normally do it. So I've got the R slots, and then I've got n minus 1, gosh darn it, n choices for that one. And I tend to put it below. Let me put it below. N choice for that one. N minus 1 for that one. N minus 2 for that one. N minus 3, and so on. If you'll notice, we got to figure out where we stop. Of length 1, I'm subtracting 0. Of length 2, I'm subtracting 1. Of length 3, I'm subtracting 2. So of length R, I'm subtracting R minus 1. Minus R minus 1. It's minus R minus 1. in parentheses. So when you distribute that negative through the parentheses, you get a plus 1. Okay? Now, that's a slightly different setup, but it does have a nice structure to it. As and what I would do is I would now throw in, what we're looking at here is kind of like a factorial, but we're not taking it all the way out to 1, right? Well, let's go ahead and throw those parts in. So I keep going until I get to n minus r plus 1. That's the last one. But then the next one, well, subtract 1 would be n minus r, and then there's n minus r minus 1, and you keep going down to 1. Okay? Well, I threw in a bunch of factors here I didn't need. Everything from this point over I didn't need. And you'll say, well, why did you do that? Well, it's so I can write it with factorial. So let me get rid of them. Right there. What we've really got here is n factorial in the top. These parts here are all going to cancel out. This is n minus r quantity factorial in the bottom. Okay? Which can be a much nicer way of keeping track of the number of ways this happens. Let me underline. Okay? Things of length r made of n items that cannot be repeated, we have a special name for that. We call those permutations. Okay. The number of permutations of length r from n items, which we will denote with a big P here, capital P, and then n comma r. It's not the best notation in the world because we also sometimes use capital P as probability, but hopefully we'll understand in the context of what we're doing which one of these notations we're talking about. We haven't done a lot of probability anyway, but I'm just saying that is probability notation. Denoted in permutation in pick r is the way I tend to think of that. Your book doesn't use this notation, but I've seen this notation quite commonly, is n p r, where the n is a subscript in front of the p, and then the r is a subscript after the p, which would be read n pick r. Okay. Pick because we're putting them into an arrangement and they're distinguishable items. Okay. But that number is given by, and it's just exactly this arrangement up here. I'll stick with this notation because it's the one that your book uses. But this is n factorial over n minus r quantity factorial. Okay. So if we're talking about permutations, that's the the number that we want to calculate. Now, I'll be honest with you, to calculate it, you probably still use this technique of just multiplying these things up. It's just this helps you know which things do you need to multiply together. The problem is that factorial gets really big really fast, and most calculators like the one I have, or like your TIs or something like that, 69 factorial is just about as big as they can handle. That's it's like 1 or 1.7 times 10 to the 98, which most calculators will go to 100 decimal places or 100 digits, and that's about all they can handle without overflow. So it's okay, that we go ahead and just multiply things out. This is just a way of reminding us what we need to multiply. Okay, kind of a shorthand way of writing this right there. Okay? So, for an example of where permutations come into play, let's answer this question. How many different ways can you have first, second, and third place finishers in a race with 100 participants? So let's think about what we're doing. There is an order to the placement, right? We're not just taking 3 people out of the race. We're taking a first, second, and third place person. So even if we had the same 3 people, if I list them in different order, that's a different outcome, right? Once someone has finished in one of these positions, I cannot use them again. They can't finish both first and second, for example. So what we're talking about here is 100, pick 3, which is 100 factorial, which you do not want to plug into the calculator, over 100 minus 3 factorial. This is 100 factorial then over 97 factorial. But what we really want to do to calculate this is, okay, from 97 on down, those things cancel out. And so this is 100 times 99 times 98, which is exactly what you would have gotten if you wrote, here's your slot for first place, slot for second place, slot for third place. How many choices do you have for the first place finisher? 100. Then after you do that, you've used up one of your choices. How many choices do you have for the second place finisher? 99. And then how many do you have for the third? 98. So it seems like we're doing a lot of work for nothing, but yet it does help us see exactly what our answer should be, and then it's going to help us move to a different situation in just a second. I used my calculator on this earlier. This is 970,200. Okay, different ways you can have a first, second, and third place finish in a race with 100 participants. Okay? And you'll see some problems like this in your homework set. So the last thing I want to tackle today, we're getting a bit of content here, but I want to throw one more little curve at you, and that is to ask the question, what if order does not matter? Now, it clearly did when we were talking about first, second, and third place, but we can also talk about situations where it won't matter. What if I just need to get a a committee of 3 together, and I've got so many people in my organization. I can't reuse people, so it's similar to the permutation problem, but yet it's not like a first, second, third. Now it's different if I ask, okay, how many ways can we install them as officers on a committee? That's a different question. But if I just need 3 people, there are 3 people, right? One of the situations we're most used to where the order doesn't matter at all is with sets, right? So let's work a set problem and let's reason through what we're going to do. So how many permutations of the elements A, B, C, D and with permutations, order does matter. Okay, so for the moment I am counting order. How many permutations are there of length 3? Okay, well, it's easy to get that number. I've got 4 things to choose from. I'm going to pick 3 of them. So this is 4 factorial over 4 minus 3 factorial. So that's just 4 times 3 times 2, which is 24. Okay. And so if I were to write them out, let's see if I can do that. It's a small enough number where I think I can write them out. So let's see. Let me leave out the D element and just build things with A, B, C. So I could put A first and have B and C follow. I could have A first and have these in reverse order. I could have B first and then have A and C, or B first and have that in reverse order. C first and have A, B. C first and reverse the order. Okay, now let me leave out the C. So A, B, D, or A, D, B, or B, A, D, that's right, I'm bad, or B, D, A, or D, A, B, and D, B, A. Or I could leave out the B. A, C, D, or A, D, C, or C, A, D, C, D, A, or D, A, C, or D, C, A. Or maybe I leave out the A. So I get B, C, D, or B, D, C, or C, B, D, and C, D, B, or D, B, C, or D, C, B. I think you can see pretty quickly that there's no repeats there, and that takes care of all 24 of the different permutations of the elements A, B, C, and D of length 3. Now, what if we remove the order by asking this question? How many groups and I don't mean groups in the, abstract algebra way, how many groups or collections of size 3 can be found? Okay. Well, now if I just start worrying about are things in the group or not, you'll notice that all of these would be the same collection, right? This would be the collection with A, B, and C. This would be the collection with A, B, and D. This would be the collection of A, C, and D, and the collection with not A at all, but B, C, and D. In other words, and actually what we're asking here is, okay, how many subsets of length 3 or of size 3 can we get out of this set? Okay, where we don't care anymore about what the order is. We're just concerned, is it in there or is it not? Okay. Note that these 6 things, if I'm looking at something of length 3, there are 6 ways to arrange those 3 things. Okay. In fact, that's 3 factorial, right? And that leads us then to a counting technique called combinations. Okay. What I would have done to get this number is I would have divided by the 3 factorial, the 6. 24 divided by 6 gives me the 4. Right, and I want to kind of differentiate there. Okay, we call an unordered group or collection of non-repeated items a combination. And that's perhaps a slightly poor choice of words to describe this. A combination lock actually doesn't have a combination, although we say that. Using this kind of terminology, it actually has a permutation of the numbers, right? Because you have a first number, a second number, and a third number. It does matter with the combination lock which order you put those numbers into it, correct? So that's just bad terminology, I guess. Either they messed up or we didn't do a good job naming this particular thing, but it's the mathematical standard, so I'm going to stick with it. The number of combinations of length R from n items denoted, so in keeping with our previous notation, C, N, and then choose R. Sometimes you'll see this, N, C, R. Okay, instead of a P, we've replaced that P now with a C for combinations. But the most standard notation in mathematical settings is to use brackets and stack the N above the R. And that is typically read N choose R. Okay. Is given by N choose R. It's the permutations N pick R but then we divide out the order, if you will. Right, with 3 things in there, we divided by 3 factorial. With r things in there, we would divide out r factorial. And so it's the same formula we had before with the n in there. Now in the denominator we've got r factorial, and then we've got from the permutation side n minus r quantity factorial. Okay. All right. So let's work one last kind of combinations problem to make sure you're familiar with what we're doing. An example of this would be something like how many, notice how this problem is rephrased from the permutations problem. How many different ways can you have a committee of 3 members from a club with 100 members? Okay. Now this is different than asking how many ways can we have a president, a vice president, and a secretary, right? Because those are categories, those distinguishable categories that put things in a particular order when we make those choices. Here we're just saying committee members. All right. So this is going to be 100, choose 3. So again, 100 factorial, and then you've got 3 factorial, and then you've got 100 minus 3 factorial. And again, this is not the way to calculate this number. If you're doing it by hand, you want to get rid of the 97 factorial. 99 times 98 times 97 factorial. Well, there's your 97 factorial. Those are going to be gone. And then 3 is 3 times 2 times 1. So 3 goes into that 33 times, and 2 goes into that 50 times. And so you can calculate that way. Also, on your calculator, you've got under, oh gosh, I should have looked before I jumped on this one, but under, it's either under stat or math, and I'll show you in class because I forgot to look ahead of time. But you can do this 100 choose 3 by putting in the 2 numbers, and then it just takes care of it for you. I did this ahead of time on my calculator. It's 161,700, which is the same number we had for the previous thing, though divided by 3 factorial. Okay. Okay, so your homework, then, let's talk about your homework. We'll have you using these things individually, and then also, in some cases, combinations of these things. Example, we want to use a committee that had so many of our male club members, and then so many of the female club members. We'd have to pick them. Those are distinguishable items, right? Male, female, usually anyway. And then so you'd have to pick those, the guys, and then pick the girls. So you end up doing this for the individual choices, but then use fundamental counting principles, say, well, this many ways to do the guys, this many ways to do girls, and so forth. So in 4.2, let's do the problems 2, 3, 6, 7, and 8. And those have some parts to them. And then in 4.3, do problem 5, and then problems 8 through 11. Okay. They'll give us a little practice using this. I suspect many of you have seen these things before. In fact, a lot of times this will be called a binomial coefficient. So if you've had any statistics where you talked about the binomial distribution, you've seen this little bird before. Okay, we're going to use it in a slightly different context here in counting stuff up. Okay, all right, that is all of that, and I will let you get to those problems. We're going to work these problems in class on Thursday. Okay, so I'll see you then.